All right, in part 2 of this section 4.4 examples, we're going to go over prime factorization. So here we have numbers like 60, 72, 105, 256. And what you want to do is find the decomposition of primes that makes each of the numbers. So there's an exercise that you can do to do that, and it's just like check from the smaller divisors to the biggest. So for example, you pick 60, and you say, can you divide 60 by 2? And 2 is the first prime. So if that is true, then you can check what is the next number that you get. So if you divide 60 by 2, you're going to get 30. Can you divide 30 again by 2? And so, yes. And then you're going to get 15. So what is the next prime that you can use? Can we use 2? No, 2 is not going to divide 15. Can we use 3? Yes. And so 3 divides 15 and you get 5. Now 5 is another prime. And it's not divisible by 3, so you gotta use 5 to divide it, and then we reach to 1. So in this way, we kind of find all the possible divisors that we can have for the number. And so in this way, we can represent 60 as 2 times 2 times 3 times 5, which in powers will be 2 to the 2 times 3 times 5. So 4 by 3, 12 times 5, 60. Your multiplication should give you the number at the end. We can do the same thing like for 72. So 72 divided by 2 is going to be 36. So we can actually divide again 36 by 2. And we're going to get 18. 18 can be divided again by 2, and we're going to get 9. At this point, we cannot divide more by 2. So we try by 3. 9 divided by 3 is 3. And we can divide 3 by 3, we get 1. So we can represent 72 as 2 to the 3 times 3 to the 2. This is the prime decomposition. Now that you know how it goes, then we can also find different decompositions. So sometimes it's not going to work immediately. So for example, 105 doesn't really have anything that you can do with 2. So you got to move to 3. And so in 3, you can go with, okay, 3, we divide by 3. 3 by 30 is going to be 90. And then we have 15 more, 105. So you can pretty much go with so 30, 33. Yeah, 35. So 35 and 35 by 3, yes. 35 by 3 cannot be divided, or 35 cannot be divided by 3, but you can divide by 5. And then you get 7. 7 cannot be divided by 5, so you tried 7, which is another prime, and you get 1. So once again, this is 3 times 5 times 7. And that's the process that you will usually go through when you're finding prime decomposition. Sometimes it's just going to be simply one single prime. So for example, 256 is just going to be 2 to the 8. Because if you start dividing 256 by 2, then it just divides, this is 128, and then it's 64, and then it's 32, and then it's 16, and then it's 8, and then it's 4, and then it's 2. That way you get all the powers of the primes. Okay, so now that we have these numbers, then we can talk about finding their greatest common divisors. So for example, doing the decomposition with the numbers that we got, since we got that the decomposition of 60 is 2 to the 2 times 3 times 5, and we get the 72 is 2 to the 3 times 3 to the 2, then the greatest common divisor is just going to be the primes that you have in common the common powers that you can have. So for example, here you have 2, and the common power that they can have is 2 to the 2, so 2 to the 2 times 3. Also, because you have 3 and 3 square, so 3 to the 1 is going to be the biggest power that is common between them. 4 times 3 is going to be 12, so the greatest common divisor between these two numbers, it will be just 12. Now for 105, 135, 105, we determined that it was 3 times 5 times 7, and 135 we can classify as 3 to the 3 times 5 when you do the composition. So the greatest common divisor between 105 and 135 is just going to be, of course, 3 times 5. Common 3, the common power is going to be 1. Common number 5, power 1, so 15. So now that's the way of finding the greatest common divisor. Now let's talk about some proofs again. So we want to prove that for all integers n and n plus 1 have no common divisors larger than 1. So in other words, consecutive integers are relatively prime. So here we're going to use something that is called a proof by contradiction. So we're going to assume that there is. So by contradiction, assume there are common divisors between them. So there gotta be, and then it says a d that belongs to the integers with d bigger than 1, so that d divided n and d divided n plus 1, since it's a common divisor. But then because d divided two numbers, then it's going to divide also the subtraction. We proved recently that if we divide two numbers, then we can divide the subtraction. So pretty much this says that d divided n plus 1 minus n, and so this will mean that d divided 1. But the only divisors of 1 are plus or minus 1. So d should be plus or minus 1. And this is going to contradict d bigger than 1. Now let's go with some true or false questions and make some justifications here. So if a and b, and a divided is b and c divided is d, then ac divided is bd. And this is actually going to be true. We're actually going to prove this down here in question number 12. So let's do that first, and then we'll come back to that question. So the way that this happens is if a let's go with a direct proof. So step number 1, my assumptions: a divided is b, c divided is d. So step number 2, definition of the assumptions: b is equals ak, and d is equals cl, with k and l that are integers. So now I want to say things about BD. So the natural thing will be multiplying these two things. So I'm going to multiply B and D. B times D is just going to be equivalent to having AK times CL. I can group things together, and I can just do A times C groups with KL. Now, because KL are both integers, then the multiplication that I'm going to call R is also an integer. And so this is going to be my step 3 manipulation. And I'm going to arrive to my step 4, which is going to be AC times R. So this is the definition of the conclusion. We have that BD is AC times R with an R that belongs to C. And so conclusion, we have that AC divides BD. Okay, so with that, we know that this is true. Then now let's come back to question 11. So we had that this is true, and this is question 12. Now, for B, we have if A divides B plus C, then A divides B or A divides C. And this is false, because in particular, you can have something like 3 divided 1 plus 2, which is 3 divided 3, right? We know that this is true, but we don't have that 3 divided 1 or 3 divided 2. We're just not going to have this. So let me just put an or instead, since I'm doing negation. 3 doesn't divide 1, 3 doesn't divide 2. Now, for C, we have if A divides BC and A is prime, then A divides B or A divides C. And this is actually true. And this is what we call the Euclid lemma. We actually proved this in class. So just remember that this is true. If A divides the product of two numbers and A is prime, then it's because A gotta divide one of those numbers. Okay, let's move on to question 13. So now we want to explain why the fundamental theorem of arithmetics guarantees that the prime factorization of any integer bigger than 1 is unique. And so in general, what's going to happen is that if you have another representation of prime factorization, so for example, if n is bigger than 1, the fundamental theorem of arithmetics says that it can be represented as p1 alpha, p2 alpha 2 times p3 alpha 3 times pn alpha n. If you have, because these primes are distinct, so if you have another representation, if n is equals some different primes, you have a different primes that supposedly are giving you the same representation, what you're going to end up having is that pi to the alpha is going to be equals to qi to certain alpha. And so we're going to have that one prime gotta be equals to another from the other list. So they might be in a different order, but that's it. They cannot have different powers, because if let's say there's a prime that is represented as different powers of another one, then that will make it so it's not prime. So that's why this is going to imply that if you have two different representation, then that representation is because they're just switch around in terms of their prime representation. Now, for question 14, we have that if 3 divides n squared, then 3 divides n. And so here we can prove this by using contrapositive or by using contradiction. So it's much more easier, let's say, by do direct proof by contraposition. So this will be if P implies Q, but then instead we're going to use the equivalence of proving not Q implies not P. So that will mean that if 3 does not divide n, then 3 does not divide n squared. So if we assume that now here for the first one, if 3 doesn't divide n, then what we're going to have by the quotient remainder theorem is that n is 3q plus some remainder. And you got to remember that that remainder got to be between 0 and 2. It cannot be bigger than 3. So this is going to be split in 3 cases. Case number 1 is 3k plus 1, or case number 2 is going to be n equals 3k plus 2, or case 3, n is going to be 3q, and that's it. So now if we have that this is 3q plus 1, then n square is just going to be 3q plus 1 square. And so this is going to be 9 q squared plus twice this, so 6q plus 1. And which this is something that you can see as 3 times 3q squared plus 2q plus 1. So it's pretty much, as you can see, it's also not divisible by 3, right? Sorry, we only have 2 cases here. It cannot be 2, 0, and 2. It can just be plus 1 and plus 2, the residual. Because 3 doesn't divide n, then we cannot have the case where it's 0. So because 3 doesn't divide n, r equals 0 is not possible. So we only need to worry about 2 cases. So notice that if n squared is represented in this way, then clearly 3 doesn't divide n squared. Because otherwise it will be just n squared is 3 times something, not 3 times something plus 1. Same thing with this. If we do n squared here, then we have 3q plus 2 squared. And we're going to get that this is 9q squared plus 12q plus 4. And then we can do exactly the same thing that we did before. 3q squared plus 4q. And then here plus, sorry, a plus 1 in here. Plus 1, 3, and then a plus 1 here to make it 4. So 3 by 1, 3. And because we have 4, then plus 1. But as you can tell, then once again, 3 is not going to divide n squared. So this way we prove that the contrapositive is true. And so we prove that this is the original statement is not true. It is true, sorry. If 3 divides n squared, then 3 divides n. Now for question 15, we have, is it possible for an integer to have exactly 3 positive divisors? If so, give us an example of such integers. And yeah, so we do have an example of that. So consider n equals 4. N equals 4 has divisors 1, 2, and 4. Okay? 1 counts, and this is exactly 3 divisors, 3 positive divisors. In general, an integer has 3 divisors, even only if is the square of a prime number. So it's like n is equals p squared. In that case, you're going to have that is divided by 1 by p and by p squared. So that will be the general statement there. Okay, so this concludes the examples for section 4.4. Make sure to check in more detail the solutions documents if you want to once again go over this in more detail.